Hi everyone, so this is Carrie. Today I'll be talking about something fishy in the CSM asymptotic analysis worksheet. So for all of these questions, we'll have to give a tight asymptotic runtime bound for each of the following functions. And we can assume here that when we mean array, we mean an m times n matrix, where m is the number of rows and n is the number of columns. Okay, so let's get started. First we have this method public static int red herring that takes in a two-dimensional array. So we see here that in this if case, if the array.length is less than 1, or if the array index 0.length is less than or equal to 4, then we immediately return 0. So if this array fits either of these qualifications, we will return immediately. So in this case, this will be a constant time operation, so thus we know that the best we can do, as in like the big omega, is constant. So if this if doesn't evaluate to true, we go on to the for loop. So here this for loop will first iterate through all of the rows here, and the second for loop, the inner for loop here, will go through all the columns. So if you notice here that it says if j is equal to 4, return -1. So we'll see here that even if n, this value n, which is array I.length, even if this value is, let's say, like 1 billion, no matter how large it is, as soon as we reach this if statement, once it reaches 4, we will return -1. This means that this inner for loop only runs a total of 4 times before returning. So really, the maximum that the maximum amount that this for loop will ever run, it will only run a maximum amount of 4 times. Oops. So only run a maximum of 4 times, and as we all know that this is basically just constant time because 4 is a constant factor. So we see here that this big omega and this big O are the same value, thus we can say that its big theta is constant. So now we moved on to crimson tuna, which is also takes in a 2D array. So again, we see here that if array.length is less than 4, we return 0. So that's just a constant time operation. So we know in the very best case, this is just a constant time method. But then for the for loops, we see here that the for loops are exactly the same as before, except in this if statement, we're saying if I is equal to 4, not if j is equal to 4. So how does this change how this for loop runs? So before we stopped when j is equal to 4, but now we want to stop when I equals to 4. So that means we have to run this for loop a total of 4 times to completion. So that means that we want to run it n times, like 4n times, because we want to run it until this I is equal to 4. So we will run this inner for loop to its completion from 0 to n 4 times. So what that means is that the big O is 4n, where n is the number of columns, as we said here, and with this big O of 4n is the same as big O of n. So we see here that the big omega is constant and the big O is n, so these two are of different magnitude, so we cannot say that there is a big theta, and instead we say the big O is big O of n. So next, let's do pink trout. So we see pink trout takes in a number a. So we see that if a is mod 7 is equal to 0, meaning a is divisible by 7, then we immediately return 1. Thus we know if our input is ever a multiple of 7, we'll just immediately return 1, so we know that's a constant time operation. So this means our big omega is just 1. So let's see an example where a is not divisible by 7. So let's say we input 13 here. So we see, is 13 divisible by 7? No. So we go into this else, and we want to do a recursive call on pink trout with a minus 1 as the input. So we'll run a recursive call on 12. So we'll go here again, like, is 12 divisible by 7? No. Go into this else, and we run this recursive call again with 11 as the input, so 12 minus 1. We'll do it again, is 11 divisible by 7? No. Go to this else. So you run this recursive call. We keep running it with the same pattern. So we'll keep going and going, but then eventually like here we've hit 7, so we see, oh, is 7 divisible by 7? Yes, so we'll return 1. So as you can see here, no matter what number we input here, we will run this recursive call a maximum of 1, 2, 3, 4, 5, 6 times. So the most recursive calls this will ever make is just 6. So our big O is just 6, which is constant time. So again, because our big omega and our big O are both constant, we can thus say that our big theta is also constant because the big omega and the big O match. Alright, so now let's do Scarlet Koi, the last question, which takes in an int array, sorted array, and 3 integers, x, start, and end. So this is a recursive function, and it looks a lot like binary search, but it's a little bit different. So this is its base case, and if this expression doesn't evaluate to true, then we jump to this line here. So here we calculate this integer mid, which is the n plus the start minus n divided by 2. So then, as you can see here, this method returns a Boolean, so we want to evaluate these 3 expressions and return either true or false. So because these expressions are all OR together, we can do what is called short circuiting, which means that if any of these expressions evaluate to true, we can immediately stop evaluating them and just return true. Because for ORs, if we just have one true, then we know the whole statement is true. So here first we can we want to return sorted array mid is equal to x. So we see here that in this sorted array, if the middle index is equal to this x value, then we will just return true immediately. So again, if the sorted array we input, if its middle element is x, then we will just return true, and that is a constant time operation, because all we'd have to do is calculate this middle and check to see if the middle element is equal to x. So what if this one does not return true? Then we have to evaluate this recursive call, Scarlet Koi. And as you can see here, Scarlet Koi will recurse on the left side of the array. However, if Scarlet Koi also does not evaluate to true, we will have to also evaluate this Scarlet Koi method. So in the worst case, we will have to recurse on both sides of the array, and we will effectively have to look at every element in the array. So thus the worst case here is O of n, where n is the size of the sorted array, because in the worst case, we will have to recurse on both sides and thus look at every element in the array. So here, why can we only give a big O runtime and not a theta runtime? So we can only give a big theta runtime if the big omega and the big O runtimes are the same, so if they have the same magnitude. So here we see that big omega is constant and big O is of n, so thus we know that they're not the same, and that's why there is no big theta runtime.